Welcome back to Symmetries in Quantum Mechanics. In the last lecture, we effectively concluded our investigations of the consequences of Shor's lemma, and we arrived at quite some interesting results, namely that characters of a representation carry a lot of information about the place of irreducible representations in a bigger representation. So the story so far is we have a group, G, an abstract group of labels. These labels label symmetry transformations of our quantum system. So we have a quantum mechanical system characterized by a Hilbert space H. And our symmetry group acts via symmetry transformations. That's effectively the axiom of this course, is that symmetries in quantum mechanics are symmetry transformations in the sense of Wigner's theorem. And that delivers us a unitary representation of the group on this physical Hilbert space H. So far, so good. That's what it means to do the symmetries on the quantum mechanical systems. It means you must have a representation. That means that the identity means doing nothing label means do the identity, and the identity of the group should correspond to doing nothing. And if you have one symmetry transformation with label S and then followed by other way around T and then followed by S, then that's just the same as having composed the labels first and then doing the symmetry transformation. This U means that we're focusing now on unitary representations. Unitary means that rho S dagger, rho S is also the identity. This is a very general setup because any symmetries in quantum mechanics you could be interested in will form a group, well, mostly, and any Hilbert space can play the role of this representation space here. So this is super general. It covers almost any possible imaginable scenario in quantum mechanics. And we've learned that these representations here, the ones furnished by such Hilbert spaces, we've learned some things, right? We've learned that these always decompose into a direct sum of other smaller atomic Hilbert spaces. Now, I'm just checking. I want to get the notation right when I continue on here. So I'm going to pause for a moment to check the notation. Yeah, okay, we'll go with that. So J equals 1 to K. We've learned that our Hilbert space always breaks up into a direct sum of smaller Hilbert spaces where Mj is an integer, a positive integer, a non-negative integer, sorry. And Wj is an irreducible representation of the group G. So this tells us, that's what we learned in the last lecture. Effectively, we got that far. We learned that, yeah, sure, it's possible for symmetries to act on a quantum mechanical system, but only then when your Hilbert space breaks up into a direct sum of these irreducible representations. So there's a couple of consequences you can learn from this. If your Hilbert space is too small, then some of these representations can't be there. There's obviously some arithmetic rules about how many copies of each one can fit into your Hilbert space. If your Hilbert space is infinite dimensional, of course, there's an infinite number of copies of each of these if your group is finite. There's a lot of things that you learn already from this decomposition theorem. Before I move on, I just want to write this in a different way because this different way turns out to be exposing a much more general result about finite dimensional C-star algebras that we won't have time to talk about in this course. Oops. Namely, just by using the tensor product, we can write this decomposition in a different way. And this different way turns out to be very, very interesting later on in more advanced applications of symmetries in quantum mechanics. So what does mj times by wj mean? It means that in this direct sum decomposition, I have mj copies of wj. But another way of saying that is that I've got the vector space C to the mj tensor with wj. Now we learn something super deep. Even though it's just an almost trivial rewriting, we know how, yeah, I guess I'll go on a tangent for a little bit here on this decomposition, because that's very helpful for understanding how these symmetries actually act. Okay. This second way of writing things is very, very evocative. Before I move on to explaining why I find this very, very interesting, I should just, of course, set the notation. I didn't quite do that. Namely that wj, for j equals 1 to k, are all irreps of G. Today we're going to answer the question, how do we find these irreps? How can we build these irreps? But for the moment, you just have to believe that someone's gone away and worked hard and worked out all the irreps. Yep.
I have a question. The dimension of this C space
yes.
is just the coefficients from our irreducible representation of G, and the tensor is like the irreducible representation of G. Just in order to get this.
Oh, okay. Good. I guess I'm going to explain the answer to this question. It's a good question. So the question is, this tensor here, is this the tensor product I explained earlier about, I explained that if you have two irreducible representations of a group, you can always get the tensor product of their representations, and that gives you another representation. It's a different tensor product. This is just the linear algebra tensor product here. I mean, technically, it's also the second interpretation, as you'll see in a minute. This is just a linear algebra statement. What is this thing here? mj, wj. Well, that's just wj direct sum wj direct sum wj mj times, right? But another way of realizing that direct sum vector space is just as the linear algebra tensor product of C to the m tensor, that vector space. Okay, now, we're going to learn something interesting already. Because of Shor's lemma, we know that rho, when it acts on one of these wj's, one of these irreducible representations, how does it act? Well, like the identity. It's just the identity. Rho is the identity. I'll rewrite that just so it's a bit less ambiguous. If we have an irreducible representation of our group, rho, how does rho act? Well, rho acts as the identity. Okay, that's a bit more concrete. So now we can ask ourselves, how is rho acting on this big Hilbert space? So let's draw a picture of this action. This is already, we can see that rho has a certain structure, and we're actually going to effectively prove this later in the lecture. So if we now look at the representation that we have right here. We could ask ourselves, what sort of matrix is rho? What does it look like? Well, it's a matrix. I'm going to take a block decomposition of this matrix. Here we've got C to the M1 tensor W1. See, we've got a direct sum. We could call these, I don't know, Yj. Right, these subspaces. This is a direct sum of subspaces. So this is block Y1, this is block Y2, and so on. Now, as a consequence of Shor's lemma and all those corollaries of the previous lecture, we know that rho doesn't map between these blocks. All rho ever can do is do something in here, right? It definitively has to be 0 between all these other blocks. But we actually learn, and so, okay, good. That's how it looks. Huh? Now I'm going to give these a name. I'm going to call this block matrix sigma 1, this is sigma 2, and so on. So our symmetry acting on our Hilbert space breaks up into a direct sum of unitary transformations, sigma 1, sigma 2. These have to be unitary because this is block. And the unitarity condition means that each of these sigmas is unitary. But now we can look at this decomposition here and we can say what kind of things, how can sigma 1 act? Well, or sigma j. Sigma j goes from sigma j acts on this subspace yj, right? Gave it a name. Now, on this decomposed vector space here, it has to act as the identity on Wj because of Shor's lemma. Wj is irreducible. So the only way sigma j can act is as some other matrix, which we'll call tau j, that can depend on the group element, so S, but tensor as the identity on Wj. Okay, so we've learned something. We've learned that the way our symmetry acts on a quantum mechanical system is, well, as the identity on each of these irreducible factors, tensor some action on this multiplicity space. It has a name, it's called the multiplicity space. And this turns out to be extremely useful in applications, this realization. Actually, this is a shadow of a bigger result, a more substantial result emerging in the study of so-called C-star algebras. If you have a bunch of matrices, finite dimensional matrices, and you form an algebra with them, that means you add all together all their sums, and then you take products, and you add the products and sums and so on until you get a closed set of matrices. Those matrices form something called a finite dimensional C-star algebra. And any such matrix, collection of matrices can be rotated to have this form here. This is a very general result. Non-trivial to prove that in general. We're going to effectively prove this in the group setting. And what we have here is an example of this representation theory. And in the case where the matrices are so-called group C-star algebra operators. So and this result tells us a lot about, for example, in finite dimensional quantum information theory, this is the no cloning theorem or the generalized no cloning theorem. And it has lots of consequences now for communication theory and so on and so forth. So this is very useful in so-called quantum Shannon theory and entropy, quantum entropies. There's many, many applications of this decomposition here. Coding theory. So I haven't proved this decomposition even in this group C-star algebra setting here, but I'd argued it, right? I'm a hop, skip, and a jump away from having proved that decomposition there. All right, so that's kind of like a fast forward snapshot to the end of this lecture course. That's sort of where we want to end up. And I can already tell you where we want to end up at this stage because all the symbols make sense to you now. The only thing remaining is sort of filling in the gaps. Now, one of the things I wanted to highlight here at this point was that the incredibly important role of these irreducible representations here. Once you know them, then everything else is built from them. These are the atoms of representation theory. And therefore, it's very important for us to build them, understand them, list them. You know, every symmetry group you care about, there should be, best case scenario, there should be just a book where you can look up these irreducible representations. There is such a book. You can go buy it. It's a big, thick book. And it's on paper as far as I'm aware. But of course, I think in the meantime, it's all been digitized. So any group that you care about, most likely someone's worked out all these WJs. So you just Google, if you end up with a group and you say, oh, it's the so-and-so 24th half monster group, blah, blah, blah. And then you Google representations of the 24th half monster group, blah, blah, blah. And then someone will have written down these representations. So it's a tabulated solved problem for all finite order groups. For infinite groups, of course, it's wild, wild, wild west, and not as much as known. But that's, we're not talking about infinite groups in this course, although I'll touch on it in the last lecture. Now, but what if you don't want to do that? Or what if you want to understand how people got these irreducible representations? Where do they come from? Well, the answer is, sort of, I think pretty dramatically, we already have a way to get at them. We've already defined a thing that has all of these irreducible representations in it already. And it's like a bit surprising that, it's a bit surprising that what I'm about to write down would work at all, but it does. And I'm going to show you, I'm going to prove it to you in like a sequence of really, really, really short proofs how we can get at every single irreducible representation of a group, knowing only the group multiplication table itself. All right, we're going to need some notation. We're going to call by chi 1 through to k the corresponding characters of these irreducible representations. No, character is just the trace of the representation. And now, where are we going to find these irreducible representations? Well, one strategy would be to find a nice big representation that was somehow easy to work with, and then hope that every possible irreducible representation somehow appeared in this decomposition here. Turns out that's exactly the case, and the representation I'm talking about is the regular representation. It couldn't be easier. That representation alone already has every single irreducible representation inside it. So remember how the regular representation works. So we have our group G. We introduce a basis E T such that T for every element of the group. I'm going to further assume that this basis is orthonormal per definition, right? Okay, I'll just do that. And then how does the regular representation act? Well, if you apply it to one of these basis kets, then you get another basis ket, namely the one associated to ST. I guess I better do an example, right? I can't remember if I did an example when I talked about this last time. Okay, I'm going to choose an example small enough that I can do everything and big enough that it's not totally trivial. So we're going to imagine we have a ring of 3 sides, or a system arranged on the vertices of a triangle, and you can't flip the triangle over. But you can certainly rotate the triangle by 2 pi divided by 3, and that's a symmetry. And so the corresponding labels are these things here. It's just a set of 0, 1, and 2 modulo 3, right, when you do addition. So that's a group. Now I'm going to write out the regular representation here. So we need to introduce 3 basis elements that are orthonormal, labeled by elements of the group. And without loss of generality, it's finite dimensional after all. I'll call by these 3 basis elements. Those are the 3 basis elements, and I attach the first one to 0. That's E0. This is E1 bar, and this is E2 bar. These 3 basis elements like that. So now we're going to work out how does each symmetry act on these 3 basis elements. Well, per definition, right, let's do the identity, that's the easy one. So what matrix leaves the basis vector unchanged? Well, we know the answer. It's 1, 1, 1. It's the identity. Now let's go to the second one, row 1 bar acting on ET, that equals E1 bar plus T modulo 3, right? Am I going to get this right? I got to add 1. I think it's this. Nope, I messed up. Other way around. Whoops. Oh, no, I think this always happens. I got to think backwards. Not very good at that. So if I have the basis vector E0, that's got to become the basis vector E1, right? So I have to make a 1 come in the middle. think it was this after all. So if I multiply this by that, I get 0, 1, 0. It works. Now if I put a 1 here, I get 0, 0, 1. Yeah, okay, that's good. Yeah, I think it's right now. And then, of course, row 2 bar is this one. 1, 0, 0, and 0, 1, 0. That one's forced on us because it has to be that when I multiply row 2 bar and row 1 bar, I get the identity. And I do. Yeah. Okay, there we go. That's the regular representation for the group Z3. And as soon as you have the group multiplication table, as soon as you know how each element multiplies by each other, it's a straightforward matter to just write out these matrices here. Okay, so we've got a regular representation. Now, the claim is the regular representation, when I look at this vector space here, what's the Hilbert space? The Hilbert space is C to the 3, it's a Q-trit. And I decompose that, I'm going to find all the irreducible representations of Z3. That's where we're going. Yo?
This method of like working backwards, I see how it works for like small systems, but what if we have like a really big group? Can we still like, because we can't guess it then, right?
Okay, so the question is, what do we do if we have a bigger group? It's sort of clear what to do when we have a tiny group, but what do we do with a bigger group? So it's an algorithm, right? So it doesn't look like an algorithm at this stage. But the input data to this algorithm is the group itself, the multiplication table for the group. You definitely need that, otherwise there's no hope. And then the entries here, you could work them out algorithmically. And then you label all your basis vectors one after the other by elements of the group. That's our algorithm. That's attaching a list of vectors to elements. And then you have to work out what entry do I put here. So the entry that I put up here, I look up in the group multiplication table and see, is the result of my multiplication this? So what I didn't draw, and probably what would have been helpful, is if I drew labels for these rows and columns. So the rows and columns are labeled by elements of the group, right? And so then you go through each entry and you ask yourself the question, is 1 times by 1 equal to 0? No, 0. Is 1 times by 1 plus 0, 1 bar plus 0 bar equal, oh poop, that should have been a 0, yeah. Is 0 plus 0 equal to 0? Yes, I put a 1 there. Is 0 plus 1 equal to 0? No. Is 0 plus, so you go through and answer this question based on it's a lookup from the group multiplication table, and it's an algorithm to put an entry in every row and column, and then you're done. So the algorithm scales as the square of the order of the group. So for a really big group, then you're out of luck, but you know, for pretty big groups, you can do this. And I don't know what your favorite programming language is, but I bet if you knew Haskell or something like that, you could do a one-liner that would take a group multiplication table and make these matrices, or a Mathematica. I bet in Mathematica you could have a cryptic one line that would construct all these operators from the group multiplication table. That would be a good sort of homework question. You know, given a group multiplication table, construct all these matrices in whatever your favorite programming language is. I bet you could do it. I bet you could do it within less than 20 lines, probably 10 lines in most languages. Because it's 2 for loops, right? Three for loops, right? I got to iterate through rows, columns, and elements of the group. So, now let's just, before we move on, let's look at the character of this regular representation. That's kind of an interesting thing. because we're going to notice something straight away from the example that we've just done here. Watch this. We're going to call this representation the regular representation, so I'll put an R there just to make that clear, that R is the regular representation. What's the character of it? Well, the character is going to be called R, and by definition it's the trace of the row of the R of S, right? Now let's wander over here and look at our little mini example, and we're going to notice something. It should jump out at you straight away. The trace of the identity is 3. The trace of this is 0. The trace of this is 0. That's no accident. For the regular representation, the trace of every element except for the identity is 0. I'm not even going to prove this because I'm going to prove it by this example, but you should see it. You should immediately, like if it's not clear to you from this example, then go back to this example until you understand it here. And the minute you understand it in the case of this example, then you'll get the proof, right? So this is obvious, right? The trace of the identity element is always going to be equal to the dimension. So the identity, the dimension of the vector space. The dimension of the vector space is exactly the order of G. Okay, that one I proved on the basis of this example. Now what about this one? Well, can there ever be an entry in the diagonal that's not 0? And the answer, yeah, that's the only thing you have to prove to yourself. So you look here, you look along all the rows and columns, and you ask yourself the question, can an entry be non-zero on the diagonal? Well, for it to be non-zero, it would mean that if I use the group law to take that entry, multiply it by that element, then I get that element back again. But there's only one element of a group that does that. It's called the identity. So whatever the group product is of this element times by another is going to be something else. It's not going to be the same element again. So it's always 0. Okay, that was the proof. So the character of the regular representation is super easy, right? It's just like G and then zeros everywhere. And now comes the wild kind of result. We actually learn, as a direct consequence of this mega simple character, that every irreducible representation can be found inside this regular representation. Furthermore, the multiplicity is equal to the dimension of that representation. So it gets found in there not one time, but nj times, where nj is the dimension of this irreducible representation. So this dark magic can be proved with a simple corollary of the thing we discussed last time. Remember this inner product I was talking about last time? Remember the cool property of this inner product? Rg is a function on the group, chi j, the character of the jth irreducible representation, is a function on the group. If you compute this inner product here, it gives you the number of times that that irreducible representation appears inside here. Well, let's write in the definition. That's the definition of this inner product. And then comes something interesting, right? We know a lot about this function. It's always 0, right? Unless S is the identity. But we even know something more now, right? So chi of the identity, that's the trace of the matrix which does the identity. Well, that's just equal to the dimension of Wj, right? So that's Nj divided G. And so what we've learned is that every irrep can be found inside this regular representation. Because remember, we started by assuming that we had the complete list of all the irreducible representations. And we now use the fact from last time that the inner product between this character and that character tells you the number of times it's in there. And then you might be worried, well, what if one of them isn't in there? Well, they're all in there because this number is always greater than equal to 0. Because Nj is the dimension, it's always a number greater than 0, G is a number greater than 0. So every irrep is in there. It's just a simple consequence of the fact that this thing is positive. So we've actually found every single representation. They're all in there. Oops, I made a mistake though. Ah yeah, ha ha ha. I made a mistake. And the mistake was, of course, that Rg of the identity here is equal to not 1, but G. So same argument, but I just messed up the factor. So each one of these irreducible representation occurs Nj times inside the regular representation. Cool. Now we can start adding up some dimensions and we'll learn some more things. we have an arithmetic relation now between the order of the group and the dimensions of various irreducible representations. So you can't have crazy dimensions of these irreducible representations. They have to obey this kind of Pythagorean relation here with the order of the group. And how are we going to prove it? Well, we know that Rg, thanks to this corollary here, has got to equal from last time we learned that every character of a reducible representation is a linear combination of the characters of the irreducible representations multiplied by their multiplicities, which we've worked out here. And this corollary we get just by using that fact and importing or inserting the element S equals the identity or not. S. So if S equals the identity element of the group, right, doing the 0 in the case of Z3, then Rg of the identity is equal to the order of the group. So it does nothing, and this matrix is the order of the group in size, which is equal to J equals 1 to K of Nj times by chi j of the identity. But the character of the identity on these irreducible representations is equal to the dimension. And the other one is just, well, exactly this relation here, but where S is just left alone. So. This relation here is tremendously powerful. It tells us a lot about the possible dimensions of irreducible representations. Let's go back to our example. We have a couple of candidates here, right? So we're looking at the group Z3Z. And we don't know the irreducible representations of our group yet. We just don't know them. But what we do know is that G equals 3. There's 3 elements in our group. And we do know that every the sum of the dimensions of the irreducible representations have to add up to 3. So I don't know how many there are at this stage, right? So we'll just say K. Now, it turns out there aren't many ways to write 3 as the sum of squares. Well, let's start by limiting K. Can K be bigger than 3? No, right? Because the dimension of each irrep has to be at least 1, and if we had 4, then 4 would be bigger than 3. No, so K is going to be less than or equal to 3. So we're looking for 3 non-negative integers n1, n2, n3 whose squares sum up to 3. Now, why do I say non-negative? Well, it could be, right, that we have only one irreducible representation of dimension 3 and the other two are 0. But that you can see is already locked out, right? Because if n, the dimension of the irreducible representation was 3, then we'd have 3 squared is equal to 3. That doesn't work. So we could have the following possibilities: 3, 0, 0 for those dimensions. We could have 2, and then one of them is 1, and then one of them is 0. Or we could finally have 1, 1, 1. So we've already locked that possibility out because the left-hand side doesn't equal the right-hand side. What about this one? Well, that's also is forbidden, right? Because 4 plus 1 is 5, and 5 doesn't equal 3. So actually, that's it. We're done. We already know that we have 3 irreducible representations of dimension 1. I haven't quite built them for you yet. The missing data is the character, and that we'll get to in this or that lecture. But we at least know the dimensions already just from this equation here. And you can play this game for any group, right? This is part of the detective work that you need to do to get to these irreducible representations. I think that's all I wanted to say on this topic. Yeah, this is part of the detective work information that we need to work out how many dimensions of irreducible representations. So I'll just put up a square around that one. No, but the second part of this corollary does give us more information, doesn't it? We learn ever so much more. I just noticed. So, okay, we've worked out this much. There's 3 representations, they're all dimension 1. But look at this equation here. That tells us more things, many more things. In fact, we're going to solve and work out all the characters of our group. I haven't prepared this, so this will potentially go all wrong. But I can't resist the challenge. Oops. The thing is, I know the answer. It's just I want to get there by using these equations. So let's continue our little detective story. So we have some information. We know we have 3 irreducible representations of the group. So there's the dimension of irreducible representation number 1 is 1. And we're going to label these irreducible representations with the labels 1, 2. It's probably better if I label them suggestively as 0, 1, and 2. So the one-dimensional representations. What does a one-dimensional representation look like? So the one-dimensional representation labeled by 0 is a number, right? It's a number. Because one-dimensional matrices are just numbers. But what's the character of a representation? It's the trace of this thing here. But the trace of a number is the number back again. So actually, the representation itself is the character for this group. The character is a number associated to each element of the group, but because this representation is one-dimensional and the trace of it is the same as the character is the representation. So we have 3 representations labeled, which are effectively completely determined by these characters, right? We've got chi0, chi1, and chi2. And we've got some equations, some pretty cool equations, which tell us that these characters can't just be any old things. They have to obey certain rules. So in fact, here we go, right? We've got 3 equations and 3 unknowns. We're in a good place right now. Let's write out those 3 equations that are in the second yellow box and the 3 unknowns, and I think we can just about do this. So we've got chi0 s plus chi1 s plus chi2 s had better equal 0 for all s not equal to the identity. Okay, I don't know if I'm going to be able to pull this off. Another little piece of detective work that we know is we know that chi s complex conjugate times by chi, oops, not s, chi whatever, L s equals 1. That's one of the properties of the character, right? Or we can just see it from the fact that this is a unitary representation. Because this is unitary, it means that the dagger multiplied by itself has got to equal 1. So it's a phase. So each one of these numbers is a phase on the unit circle. So we've got one equation. Well, actually, we've got two equations here. There's the version where there's a 1 bar in here. There's the version where there's a 2 bar in here. And there's the version where there's the identity in there, or 0 in bar. And there we get 3. 3 equations, 3 unknowns. Right, we're golden there. Oh, hang on. Sorry, more than 3 equations. More than 3 unknowns, of course. And I messed it up. Oh yeah, but we have other information. Yeah? We know that, for example, that chi naught 2 bar times by chi naught 1 bar is 1. So we have other equations. So 1 plus 2 modulating is so 3 more equations. So we've got 1, 2, 3, 4, 5 equations now. This one doesn't count anymore, right? Because we've used all that information. We know that these are 1. 5 equations and 6 unknowns. It's not looking good, right? We still got 1 unknown left. But actually, there is a final equation, which is the one I've written up here, right? And I've got 3 of those as well. So actually, I've got more equations than unknowns. So now it's just a matter of trying to solve these equations, which is a bit painful, right? Okay, these are quadratic, and that's quadratic, and these are linear. You'd be sort of a bit, you might be concerned that this is tricky. Well, okay, this is where I'm just going to write the answer down. We know it's on the unit circle. Each one of these things is on the unit circle. That comes from this equation here. So we're trying to find 3 points on the unit circle who add up to 0. So the first guess you should make is that they should be roots of unity, because when you add up the roots of unity around the circle in the complex plane, you get 0. And that's indeed, of course, what they are, right? And that's the answer. And you can check that that equation's fulfilled, that equation's fulfilled, this one's fulfilled, that one, that one, that one. So the answer is that there's 3 irreducible representations of dimension 1 of this group, and they act as the roots of unity, like so. And those three matrices that I just erased, they are direct sums of these three one-dimensional actions. In a non-obvious way, admit, but they're the direct sums. Now, I did this for 3, right, the group of order 3, but I hope now that you've seen it for 3, you can see that there's nothing really special about the number 3 that happened here. Right? 3 didn't play a particularly special role. And I hope you can imagine what would happen if I replaced 3 by n or m. You know, I'd get, well, n things here, n equations there. You know, it should be able to spot what's going to happen. In fact, the answer in general is you just put an n there at the bottom. And so we've worked out all the irreducible representations of all the cyclic groups in one go. Just by, well, you just have to put a plus dot 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 symbol, and we've actually done it for all. Interesting. So that's actually, we've done a whole bunch of very important groups. We've worked out all the irreducible representations of a very important class of groups, the cyclic groups. We know how they act, we know their multiplicities. If you just played this detective story again, you'll conclude. You'll be able to convince yourself that that's all the irreducible representations that there are. At the end of this course, maybe we'll work on some slightly more complicated groups. But already this should be sort of sufficient to encourage you to think that this is a solvable problem for more complex groups. What I want to do now is transition to observables. I want to talk about something called things called class functions. And these play a very important role in physics. A class function is an observable which is invariant under the symmetry group. So invariants play a very important role in all of physics, right? If your system or your physics is invariant under a group of symmetries, then there are things that don't change when you do the symmetries. Conserved quantities, right? You should be thinking conserved quantities. So invariants are like conserved quantities in physics. For example, when you have rotations on a physical system, you have rotations, the rotations act as, let's say, unitary operations on the Hilbert space, and there's an observable which is left invariant under this rotation action, has a name, it's the total angular momentum. This theorem, there's a general theorem in classical mechanics and also in quantum mechanics. There's Noether's theorem. It says to every conserved quantity, there's so every symmetry there's a conserved quantity. For rotations, it's the total angular momentum. For translations, it's the momentum. In special relativity, the invariant under the 4 group is the 4 interval, the invariant interval, and so on and so forth. Class functions are precisely these things in the case that your Hilbert space is the regular representation. Or they can be attached to invariants. And there's a nice connection between characters and class functions. So the first thing I want to comment is that all characters are class functions, right? Let's just check that. Right? Okay, so here you have a character of your representation. Let's compute S inverse TS. Or irreducible characters, hang on. Okay, remember we proved one of the properties of a character, irreducible character, is that it obeys this rule here. And then, sorry, I'll do it properly. Character is the trace of the representation. A representation is a homomorphism. And then you've got the cyclic rule of trace. And we can even wipe off irreducible here. So already at this sort of superficial level, we can say something interesting, namely that invariants and conserved quantities in physics have definitely got something to do with characters. But do we miss anything, right? So the question that we now want to look at is, do characters give us all the invariants, all the conserved quantities of your system under the symmetry, or are there class functions that aren't equal to characters? And the answer is, of course, there's plenty of functions that are not equal to characters. But what we will prove is that every class function is a linear combination of these characters. So these characters form a basis for all the class functions. here's something kind of new has appeared. It looks kind of like this averaging trick, but it's somehow different. This construction is something we're going to use in the later lectures to pull out certain irreducible representations from some bigger representation. So you twist your representation by this function f. It's going to turn this into a projection. You can already see that. That's the consequence of this proposition here. So if I phrase it quite a little bit more generally, but let's imagine for the moment that f is a character, right? F is just a character. So let f be a class function, in particular a character for an irreducible representation. And let's construct this weird map here, rho chi. That's the sum of these matrices multiplied by the corresponding character. Then if H is irreducible, well, yeah, we just assumed it was, then this thing acts as the identity. It acts as effectively as a projection operator. This is the building block for a much more general construction. When you have a big representation and you want to find inside it the smaller ones, then one way to do it would be to project out all the others. And one way to project out all the others is given to us now by this result. It says, well, put in your favorite character and it will pull out only those irreducible representations and set to zero everything else. We're not quite there yet, but this is a main building block towards that. And this proportionality factor is given by this number here, in which in the case of a character, right, chi is 1 for an irreducible representation. So there's g divided by n, it's just n, right, in the case of an irreducible representation. Good. Let's see if we can prove this before the end of the lecture. Well, we're going to reduce things to Shor's lemma. Namely, we're going to argue that that linear operator commutes with the group for every element of the group. So we're going to look at what happens if we pre and post multiply by rho s, this rho f thing. Well, I insert first the definition of rho f in here. Then we use this homomorphism property. Then we change variables. And then we use the fact that f is a class function. Okay. So rho f commutes with the group. And now Shor's lemma immediately tells us that rho f is proportional to the identity. Shor's lemma tells us it's proportional to the identity. So we have to work out that proportionality factor. You know, what is this number equal to? Well, we take the trace of rho f. but the trace of rho t is just a character. So we have that n lambda equals the trace of rho f. And then I think that's what I had in the proposition, isn't it? Yeah, it's good. Yeah, it worked out, right? Cool. Yep. I think I won't be able to get to the next part today, so we'll stop now at this stage. So where we have come is to the point where we've understood the beginnings of how to work out all the irreducible representations of a group. We applied that to the simple case of the cyclic groups, and we worked out all the characters and all the irreducible representations. Then we've now transitioned to these things called class functions, which are strongly related with invariants, observables that are conserved in physics. And we've used them to first construct this curious operator here and learned that it's proportional to the identity. Where we're going with this is we're going to find out that firstly that all class functions are just linear combinations of characters. And then we're going to be able to use these things, these will turn out to be projection operators or proportional to projection operators. We're going to use these things to build projections onto irreducible representations, and that's how we'll get at them all in the end. But that's the story for next time. So that's it for today. Thanks.